point 2 of lecture 9.4, we have shown that any homomorphism between two vector spaces V and W essentially is reduced to left multiplication by the associated matrix of F. The sentence is in quotes, left multiplication by the associated matrix of F, because elements of V can be anything, and left multiplication on them is not defined in general. The only reason why we leave it in quotes is because these are just sets. V and W are just sets with an algebraic structure, and the algebraic structure does not concern left multiplication by a matrix. Algebraic structures are being able to sum vectors, being able to sum elements inside V and W, and being able to multiply them on the left by scalars, by numbers, not by matrices. Of course, if V is a Euclidean space, vector space, then yes, but not in other cases. What we really mean is the following. F of V, the image of a generic vector V in the domain by the map F, is the linear combination of the basis that we have chosen of the codomain. We call this basis Wi, multiplied by coefficients mu I, where mu I, if we write them in a column vector, so mu i's are numbers, so we can write them we can plug them in a column vector, and this makes perfectly sense. So this column vector is obtained by left multiplication of the associated matrix of what? Of another column vector which represent the coefficients of the linear combination that describes V in function of the basis of the domain. This is the precise statement, and here is the left multiplication I'm referring to. Thus, up to replacing V with the lambda j's, so we replace V with just the coefficients that express V in function of the basis of the domain. So if we just consider this to be V, this column vector, and f of V, the image of V by applying the homomorphism F, we replace it with the mu i's, which are again the coefficients of the linear combination expressing this vector of the codomain in function of the basis of the codomain. The homomorphism F reduces just to left multiplication by the associated matrix, as shown here in this equality. In this lecture, we will try to visualize homomorphisms from R3 to R3. This particular case, V, the domain will be the three-dimensional Euclidean space R3, and the codomain another copy of R3, corresponding to left multiplication by certain matrices. These are all the possible homomorphisms between R3 and R3 when we express them in terms of the canonical basis, so when we find the associated matrix with respect of the canonical basis. More precisely, if this homomorphism is left multiplication by a matrix A, if we take the canonical basis of the domain and the canonical basis of the codomain, the associated matrix of the left multiplication by A is precisely A with respect of the canonical basis. I refer you to the lectures of the series 0.2 star, where star stands for certain letters A, B, C, D, E, up to E, especially to the lecture 0.2e for a thorough treatment of the visualization of functions. This last lecture of the series 0.2e deals with the visualization of functions from R squared to R squared for which we cannot draw the graph. Therefore, we have to settle with something, the visualization of something less exhaustive than a graph of a function. As seen in lecture 0.2e, in the case we cannot draw the graph of a function because that would lie in a too high dimensional Euclidean space, like in this case, the only way we can show some parts of the function we are considering is by showing the action of the function on certain subsets of the domain. We use the same coordinate system in which we represent both the domain and the codomain of the function, and we draw these subsets of the domain and at the same time its image, considering the coordinate system as a codomain. In the case we are considering now has as domain R3 and codomain R3, the graph of any homomorphism from R3 to R3 would live in R6. But already in R4 we are not able to draw anything inside, therefore, let alone R6. In order to show the homomorphism that we will consider, we will show the action of these homomorphisms on this particular subset of R3. I have drawn here a house, and a house is embedded in R3. We see as a set of points inside R3, and we will see what happens when we apply to this house left multiplication by the matrix that will be depicted here on the top right. So this will be the object to which we will apply the left multiplication by the matrix. We will not see this object in the domain throughout the animation, we will just see its image. For instance, here we see that the house has been elongated towards the x direction, and we see that the matrix is no longer the identity matrix. Here has 1.61 instead of 1. Is still a diagonal matrix, but is no longer the identity matrix. And what we are seeing here is the image of the initial house by left multiplication by the following matrix that we see. Same argument. Here we have 2.14 as a first coefficient, and the house is further elongated. What we are seeing in this animation is that when I change the first coefficient and let all the others the same, the effect I have of the left multiplication by this matrix on this object is that it gets elongated along the x-axis, both in the positive direction and in the negative direction. The YZ plane is left unchanged, as we can see here from the fact that this part of the matrix is just the identity and these are zeros. Up to 2.5 we have this elongation in this direction, and the elongation has been 2.5 the size of the initial house. What happens if we reduce the coefficient from 1 to numbers that are less than 1? Well, as expected, it gets shrinked along the x direction up to, if we have 0.03, we have just like remaining something that doesn't look a house anymore. It's almost bidimensional. This is because if you look at the rank of the matrix, this rank is almost 2. Okay, so it's still 3 just because this coefficient is non-zero, but when it will become 0, we will have just two-dimensional object which is lying in the plane generated by the column vectors of this matrix. As I mentioned in a previous lecture, the image of the left multiplication of a homomorphism by a matrix is generated by the column vectors of the matrix. In this particular case, the column vectors of the matrix generate just the plane yz, because this is the null vector, this is the 0, 1, 0, and this is 0, 0, 1. Therefore, the linear combination of the column vectors is generated just by the second and the third column vectors, which generate the yz plane. Now we are going to consider the matrices that will have the third coefficient along the diagonal that will change. Here we have again the house in the domain corresponding to the identity matrix. While we will be changing the last coefficient instead of the first, we see the effect on this house. As you can see, multiplying by numbers higher than 1 has the effect of increasing the height of the house. That means elongating the house along the z-axis. And as we shrink the coefficient towards 0, the house gets shrinked to the xy plane corresponding to the first two column vectors, the plane generated by the first two column vectors. We try to change the second coefficient of the diagonal, and well, you can probably already imagine what's going to happen to the house. Let's see if what you're guessing is correct. Yeah, is precisely this. The house gets enlarged along the y-axis this time. And the corresponding shrinked house to the rank 2 matrix we will obtain when the coefficient is 0 is this two-dimensional picture embedded in the xz plane, which is which has as a basis the vectors 1, 0, 0 and 0, 0, 1. For the next animation, it is better to change slightly the point of view. Instead of changing elements of the diagonal of the matrix, we will now change an individual element outside the diagonal. In this case, we will change the coefficient with indices 3, 1, third row and first column. And from this perspective, we can see better the action of the matrix by left multiplication on the house. As you can see, this is consistent with the theory, because if we multiply here on the right by, for example, the vector generating the x-axis, namely 1, 0, 0, we see that the result is first coefficient is 1, second coefficient is 0, and then we have a component along the z-axis which is given by 0.77. This third component gives the inclination of the 1, 0, 0 vector upwards along the z-axis. And when the coefficient is negative, the house is bent down, is tilted down. This transformation is called the shearing. Now we will change this coefficient, 2, 3 coefficient. And we get this shearing transformation. And now we will change the coefficient in position 1, 3. Now it is the z vector that is bent toward the x-axis, as we can see by multiplying on the right by the vector generating the z-axis, the vector 0, 0, 1. Now we have a more complicated transformation, and it will involve the changement of these two coefficients, the one in position 3, 2 and the one in position 2, 3. And actually also the coefficients along the diagonal in position 2, 2 and 3, 3 will be changing. So this block of the matrix will be changing, and we can see now the effect of these transformations, family of transformations. It is a rotation about the x-axis, and indeed this matrix has been computed in a previous lecture. And now, as a last family of transformations, we have some randomly chosen path inside the matrices. Same family of transformations now will be acting on another geometrical object instead of a house. It's like a torus, where we have a frame of a torus, in a sense, a frame torus. And the family of transformation is just the same as the one we have seen for the house. Okay, so now we will see the entire animation without commentary from the beginning.